All right, for my Module 7 discussion, I chose problem 7.32 out of our Mastering Engineering homework, which I think is from Module 6. And the problem reads, consider the figure below. Suppose that P is equal to a force of 6.0 kilonewtons. Find the internal forces at D, including the normal shear force and moment about D. So as you can see in the picture, I'm not an artist, so I wrote a couple assumptions just so that everything would be clear as far as the things we're working with. So here you can see that our figure, A is a pin support, which means that we're going to have two reactions, AY and AX. BC is a two-force member, so we're not having any reaction forces there. And our distances here between E to B is 3 meters, 1 meter between B and D, 3 meters between D and A. C and A has a distance of 3 meters. Here's our force of our P force, which is 6.0 kilonewtons. And right off the bat, another assumption we're going to look at is that this triangle right here, if we look at the lengths of the sides, we have a 3 plus 1 is 4, so a 3, 4, 5 triangle. So we can write this as force BC is going to be, the length is going to be 5 meters. I don't know the magnitude of the force, but we know that the length of this is 5. So the first thing we're going to do is draw a quick free body diagram of the figure showing the reaction forces. So we're going to have E up here. We have our force of P, which is equal to 6.0 kilonewtons. Then we have all this distance. We have A, and we have AY, which I'm just guessing is going this way. AX, then we have point B, point D, and then point C. We know that this is 3 meters, this is 1 meter, this is 3 meters, this is 5 meters, this is 3 meters. And we're looking for, let's just say that this is in tension, so we're going to say it's pointing this way. Force BC. All right, so the first thing we're going to look at is we're going to think about our equations of equilibrium, and we're going to come to the conclusion that because we have some unknowns with our horizontals, we have our AX, which is unknown, our P value, P force, which is known. But then we have a horizontal force segment of this of force BC. So we have two unknowns and we can't solve for. Same thing with the vertical. We have AY, we have the vertical component of FBC, and we don't know either of those, so that's two unknowns, so we can't solve there. So the easiest thing to do, and where we're going to start, is take the moment about point A, which will allow us to find force BC. So we take the moment about A with counterclockwise being positive. The moment about A equals 0. So we're going to have, so AY and AX, of course, intersect A, so we're not concerned with those. We have P, which is pointing, which would push in a clockwise manner, so it's going to be -6 kilonewtons times the distance, which 3 plus 3 plus 1 is 7 meters. And then our other force, so this vertical component of force BC would actually intersect A, so we're not concerned with it. We're going to be concerned with just the horizontal portion of it. So we're going to have, let's just say that it's going to go like this. Just dot. And this would give us a counterclockwise moment about A. So it's going to be positive. So we have plus force BC times this horizontal component, which is going to be 3/5 times the distance. Here is going to be 4 meters. So doing some simple math, we're going to get, let's see, negative 42 kilonewton meters plus 0.6 times 4, which is 2.4 force meters force BC equals to 0. 42 kilonewtons times meters equals 2.4 force BC meters. So we're going to divide both sides. And never mind. All right, so by doing some simple math with our calculator, we can find that the force of BC is equal to 17.5 kilonewtons. So I'm just going to go ahead and notate that up here. I'm actually not negative, it's just, that's what it is. 17.5 kilonewtons. Okay. So now that we have that, we can go back to our equations of equilibrium and figure out, first off, what our AX is going to be with the horizontal component and our force here. So we'll use for this. So we're going to find with going to the right being positive, f of x equals 0. So 0 equals negative ax plus 6.0 kilonewtons minus force BC times the horizontal component, which is going to be 3/5. And then this will be ax is equal to 6 minus 17.5 times 0.6, which is, let me use my calculator, 6 minus 17.5, negative 4.5. So our AX is shown in the wrong direction, that's all that means, but that's okay because we know that. So again, I'm going to put that up here. AX is equal to negative 4.5 kilonewtons, and that is with the AX going in this direction. So we know when we do our last free body diagram, we know how to notate that. And then the last portion is our, we're going to look for AY. And so this one's going to be pretty simple as well, with positive up. F of y equal to 0. We have 0 equals AY plus, minus, because it's going to be pointing down, FBC times 4/5, which is going to be 0.8, and FBC times 0.8, 17.5. 8 is 14, so we're going to add 14 both sides, and 14 is equal to AY. 14 kilonewtons. Put that up here. AY 14 kilonewtons. Okay, so now we have all of our reaction forces, and all we need to do is figure out where we want to cut our free body diagram, which is going to be right here, so that we isolate this portion and only need to work with these reactions to figure out the internal forces at point D. So let me go ahead and erase some of this. And all right, so our last free body diagram here, I used red this time, is just simply going to be point D with our normal force in the pot. We're just going to assume positive direction. Let's move this over here. We're going to have V, and then we're going to have a counterclockwise moment. And then coming down, we have A, And we know that AX is negative going this way. So if we choose to show it this way, we're going to say this is 4.5 kilonewtons. And then this is going to be 14 kilonewtons, like that. So taking our equations of equilibrium, some of the forces in the x direction. Let's see, x direction is like this. So f of x equals 0, or the sum of the forces in the x direction equals 0. Here I have it as, this is ax and this is ay. So we're going to have ax minus, plus vd is equal to 0. So ax is equal to negative vd, which means that vd is equal to negative 4.5 kilonewtons. So because ax was 4.5, we put that negative sign on the other side and get negative 4.5 in this direction. So really it's going like this, right? So, but according to how we have it drawn, and assuming positive, we're going to say that vd is equal to negative 4.5 kilonewtons. All right. Easy enough, same idea. Let's do the the y direction. So again, pointing up, positive, forces in the y direction equals 0. 0 equals ay plus md. We're going to end up with the same type thing. Let's subtract ay over, negative ay is equal to nd. So nd is equal to negative 14 kilonewtons. All right, so we're going to put normal. And last but not least, we want to find the moment about point D. So we have counterclockwise positive, moment D is equal to 0. 0 equals, so our AY is going to go straight through D, it's going to intersect it, so we're not concerned. We are only concerned about AX. And one thing I now realize is I forgot to put my dimensions in, and this distance right here is 3 meters. Let me just carry that over from right here. So AX around point D is actually going to put us in a, let's see, if we're going this way, that's going to be counterclockwise. So that's going to be positive AX times, let's see, the distance, so 3 meters. And since we know AX is negative 4.5, plus MD. So then we're going to have MD is equal to, we're going to subtract this to the other side, so negative 4.5 times 3, which is going to be, I'm going to use my calculator because it's been a long day and I don't feel like doing simple math in my head. Negative 13.5 kilonewtons. All right, and so we'll just put that right here. So our internal forces are, our shear is negative 4.5 kilonewtons, so it's actually going in this direction. Our normal at D is 14 kilonewtons in the positive direction, and our moment at D is negative 13.5 kilonewtons, so it's actually going in a clockwise direction. So those are our internal forces at point D. Thank you very much. Have a good day.